Now let's start with the physical layer, and here rather as a historical side note, it's not in the standard any longer. The physical layer of the early days of 802.11, 3 versions, 2 radio, 1 infrared, with, from today's perspective, pretty low data rates, but at these times, think that was mid-90s, that was pretty nice. So there was a frequency hopping spread spectrum, not really many products. There was an infrared version, also no products. And there was a direct sequence spread spectrum versions. There we saw many products. Different modulation schemes for 1 megabit per second, 2 megabit per second. And already these days you saw a certain way of structuring the packets. There's a preamble, a header, and those parts, they're usually transmitted with a lower data rate. And then the system could switch to the higher data rate. There were certain maximum radiated power, etc. difference in the US and Europe. So these were the early days, mid-90s, not in a standard any longer. So the most prominent legacy physical layer operates at 1 and 2 megabit per second. And you see typical packet there with a preamble and a header at the lower data rates, and then the payload could operate at higher data rates. So a long preamble synchronization is needed for gain setting, energy detection, compensation of frequency offsets. So as we will learn for the medium access, it's important to recognize, oh, there's something going on the medium. And that still is a problem if you now mix older devices with newer devices. Do the older devices and the newer devices recognize each other? That's quite important when it comes to medium access. Okay, so the single fields and the lengths, etc. are not that important, but that was the starting point of the physical layer. And then follows the so-called high-rate direct sequence spread spectrum system. This physical layer is quite prominent. It was called the 802.11b, and the 11b devices, okay, they reached already 11 megabit per second, up to 11, depending on signal-to-noise ratio, at 2.4 gigahertz. So 2.4 gigahertz, that's the ISM spectrum used for microwave ovens, etc. So this physical layer offered, for that time, pretty high data rates, but already at these times we saw, okay, the user data rate, well, something like 6 megabits per second. Why? Well, we learn with the MAC layer that there are certain gaps between sending packets needed. But also, if you only look at the physical layer, you see, okay, there's a lot of synchronization needed, depending on the packet format, up to 192 microseconds or 96 microseconds. And for the first long version, the 192 microseconds, the system operates at only 1 megabit per second using differential binary phase shift keying. And after that, the system can switch to the higher data rates. So not only do we have gaps between the packets, we need them for the medium access, but additionally, we also have headers operating at lower data rates before we can switch over to the high data rates. And this all contributes to the overall lower data rate, here for example 6 megabits per second, although you could transmit your payload at 11 megabits per second. This is also a reason why there is a short format for a packet, that's optional, but this short format already switches in the middle of the header from 1 to 2 megabit per second and then maybe over to 11 megabit per second. So you see, all these different fields needed for synchronization, signal strength, etc., header error control, and so on, they all contribute to the lower average data rates. And we are not yet talking about collisions in the medium, interference, etc. So even without interference, the data rate of those 11B systems will never reach the 11 megabit. Okay, but that was the starting point, and this was basically the standard that was really widespread. so the 802.11b. Today, all these form a separate extensions to the classical standards. They are now all integrated in the standard. So you will not find the term 802.11b any longer. So that's just the 802.11 called high rate direct sequence spread spectrum. So you will find many different physical layers in the standard today. At that time, also many users had to look at channels. So channels are quite important because you or the devices are responsible for picking a channel. There are some differences between, for example, Europe, US, Canada, when it comes to the channels you can use. So those systems, they operate in the range of 2.4 gigahertz. That's the ISM band. Industrial, scientific, medical. So that's a license-free band. So everyone can operate a device there as long as you stay within certain limits when it comes to radiation. So the output power is limited. And then within these frequencies, well, you or the systems have to organize themselves somehow. And you will find in the wireless LAN systems many channels, but only 3 non-overlapping channels. What does it mean? If you look at the channels 1, 7, and 13 in Europe or 1, 6, 11 in the US, Canada, you will see those channels are not overlapping because the channels require roughly 20 megahertz. And so if they are spaced apart, you see, okay, there's a gap, there's a guard space in between channel 1 and channel 7. If you pick any of the other channels, you will see there's a channel 2 and a channel 3 and a channel 4 and a channel 5 and a channel 6, etc. And they all overlap. So what is the problem with overlapping channels? Well, sending in a wireless LAN is not coordinated between different wireless LANs. So if your neighbor starts sending on the same channel, this transmission will destroy your transmission. If the interference is too strong, your data will be simply cancelled out. Or the interference is so high that the checksum fails. So, if you stay apart, if you use channel 1, your neighbor uses channel 7, then there's no interference. And you can send both at the same time. The point is, no one regulates this. No one forces your neighbor to pick a non-overlapping channel. So that's one part of the problem. So all your neighbors could pick exactly the same channel you pick. Then, additionally, no one forces you to stay on channel 1 or 7 or 13. So you can also pick channel 2 or 3 or whatever. So you will find many overlapping channels and transmissions. Additionally, you have so many neighboring wireless LANs that the neighbors have to use the same channels. What else can they do? So if they transmit at the same time, there will be a collision and your transmission will be destroyed. That's the whole story. So you cannot regulate or coordinate this in any way. So you can try to set up your own network if you control your network in a way that the channels are non-overlapping. So at least you and your own network do not overlap, but you cannot coordinate the networks of your neighbors, for example. So these are the classical 3 non-overlapping channels at 2.4 gigahertz. So these classical channels, they use 20 megahertz bandwidth. Today, we also have 40, 80, and 160 megahertz bandwidth. That depends on the carrier frequency, as you will learn later on. So that was the early setting. So that's not really much. 2.4 gigahertz, that's quite prominent. Bluetooth uses 2.4 gigahertz, Zigbee uses 2.4 gigahertz, so many systems use 2.4 gigahertz. So it's quite crowded there. So there was quite early already the idea, why not using a different frequency? And that's exactly what 802.11a does. A means, well, the standardization started earlier in A compared to B, but the products of B were already available when there were still some problems with 11a. So 11a uses OFDM. You learned a bit about this already. OFDM, orthogonal frequency division multiplexing, now operating 5 megahertz, above 5 megahertz. Okay, higher carrier frequency. So, how do the packets look like? Again, we have a certain preamble, and then we start with 6 megabit per second. That's already pretty high, and can then jump, especially for the payload, up to 54 megabit per second. So again, lower data rate, special symbols for the preamble, a lower data rate than for the signal part of the header, and then there's a data part with higher data rates. And the data rates available between 6 and 54 megabit per second, they pretty much depend on signal to noise ratio and what happens on the channel. So if you do real measurements, check the user throughput, you will see that for classical Ethernet packets, 1500 bytes, you will reach up to 32 megabit per second, not the 54. And you see already the reasons. We have guard spaces, we have preambles and signals, and then we can jump to the high data rates. There were some mandatory data rates. Okay, so that was the idea, operating at 5 gigahertz, but in the early users detected pretty soon that, okay, there's a drawback of using 5 gigahertz. You should know the drawback. Higher frequencies, that means lower transmission range. So the 54 megabit per second, well, maybe inside a room, roughly up to 5 meters, something like this, no wall in between. So, okay, as soon as you have a wall in between or more than 5 meters, the data rate already dropped to 48, 36, 24, etc., depending on the noise, depending on the distance, depending on the signal attenuation, etc. Again, with these systems, you could never reach the 54 megabit per second, but the usual data rates were pretty lower. But still, it was higher compared to the 11 megabit per second of the 11B standard. The operating frequencies are now around 5 point something gigahertz. And this is in many countries not a license-free band, but a license-exempt band. There's a difference. A license-free band, that means you can operate your device here. And no one can tell you, please get out of this frequency. But in many countries, around 5 gigahertz, there's also radar. Radar, for example, from airports. And maybe you can look this up in your DSL wireless LAN router. You will find something that is called dynamic frequency selection. And that is in many countries mandatory, that you check for radar. And as soon as your wireless device detects there's radar going on, operating on certain frequencies, you have to step back. You are not allowed to use these frequencies. So that's the difference to the 2.4 gigahertz. So at the 5 gigahertz, you have to use a dynamic frequency selections. So then you might not be able to use certain frequencies. But the big advantage of this 11A standard is you have many, many more non-overlapping channels. So if you look at the channels here, you can operate 36 and 40 and 44, etc., etc. Many non-overlapping channels operating at different center frequencies. So that opens up really a lot more spectrum for transmission without that much interference from your neighbors. That's exactly what you experienced in the early days of the 5 gigahertz. Suddenly, almost no interference from neighbors. That was very nice. Today, the situation is a bit different because, well, everyone uses also 5 gigahertz. Plus, today's devices, they use more than one of these non-overlapping channels, sometimes 2 or 4 or whatever, depending on the data rate. I will come back to this later. So license-exempt bands, that means you need dynamic frequency selection and you have to apply certain output power control, take care of radar. Something similar here in the US. That's just some examples. So you have more channels available and a bit different channels depending on where you operate these devices. We have the similar situation today around even higher data rates, that you can use the devices in some countries and not in other countries. So it's not the same around the globe. Just to remember, we covered this in one of the early chapters, OFDM. That means you split your data stream on many subcarriers, 52 subcarriers here, and you use 48 for data and so-called pilot carriers with pilot tones. And so you split your data stream there and transmit a lower data rate over single orthogonal subcarriers. So that was the idea of OFDM. Okay, that's a complete different technology at the physical layer. OFDM technology, already you know this, LTE. So, okay, that was an experiment, but it worked. And with higher data rates, but at 5 gigahertz, 5 point something. What followed was a so-called extended rate physical layer at 2.4 gigahertz. So that was the old 11G standard. So many devices at that time, they were called ABG devices because they supported 2.4 and 5 gigahertz, all these new standards. The data rates here, they support the classical lower data rates 1 and 2 and up to 11 megabit per second, the high rate. And then they applied additionally, if required, OFDM for higher data rates going up to 54 megabit per second. So that's similar to the standard at 5 gigahertz. So and then, well, this was basically 11A applied at 2.4 gigahertz. Then there are many more options and modulation modes, etc. But over time, some of them deprecated, obsolete, etc. Just to give you an overview of what's going on then, after this, A, B, and G, the next quite dominant standard was the 11N. 11N marketed as Wi-Fi 4 from the Wi-Fi Alliance. So it's called officially the high throughput OFDM, operating at 2.4 and 5 gigahertz. So that's fully based on OFDM. But now we can have different so-called spatial streams. So we can separate in space division multiplexing, operating at certain bandwidths, 20 or 40 megahertz per second. And this offers up to something like 600 megabit per second. So these were the devices then called, well, in the end, B and G and N and A, so that all came together. So marketing Wi-Fi 4, also today a classical standard, so all devices, they know how to handle this. And I will not go into all the acronyms of all these elements, just to give you an impression what the ideas during the development of this standard was. Well, you cannot extend an old standard for too long, but you have to be backward compatible. So, just to give you an impression, there are certain frame formats now in this, for this type of physical layer. There are, for example, the classical non-high throughput formats, because there are still devices operating at lower data rates. You have to be compatible with them. If they send something, you have to react. Or if you send something, they have to be able to react. And as we will learn on the MAC layer, it all depends on carrier sensing. Now imagine you do something the other devices will not recognize. Then carrier sensing will simply not work. So as soon as there's a legacy device in your network, suddenly this super duper new standard 11N will fall back to the old standards, and you will not have the high performance any longer because you have to be backward compatible. On the other hand, there's a so-called greenfield format. So assuming there are no old devices, so you have a green field, so there's no old device, only in the new devices, then you can operate at much higher data rates. You do not have to take care of some older devices, their restrictions, etc. Then carrier sensing works, but only for the new devices. So that's basically the idea. You integrate some way of falling back to the old technology, but if there's no old device, then you can reach higher data rates. And this is what you sometimes read, that, okay, if you want to have a higher throughput in a wireless LAN, make sure that there are no old 11B, G, whatever devices. Okay, that's by far not the end of the story. The next physical layer, as an example here, is the so-called very high throughput VHT physical layer, uses again OFDM. And that was the so-called 802.11ac standard. It's all integrated in the .11 standard. So, and this standard today marked as Wi-Fi 5 by the Wi-Fi Alliance. Now you see what is the difference. One of the difference is, well, modulation. You see here, well, modulation 64, 256 quadrature amplitude modulation. So you go to, well, more complex modulation schemes. That's one thing. Depending on the noise, the coding ratio is different. So that means how much redundancy do you have to put into your packets to be able to reconstruct the original data. So coding, redundancy. If you have less redundancy, then the data rate goes up. That's pretty clear. So for if it has to be very robust, you use the binary phase shift keying BPSK. And then depending on the so-called guard interval, GI, that's the guard interval. That means the interval between symbols. So you send a symbol 1, a symbol 2, and then you have to have a guard interval in between to avoid inter-symbol interference. That's a problem. So if you operate the devices indoors, you do not have that much multipath and reflections, etc. Then you can have a smaller guard interval. If you operate outdoor, you can have a lot of reflection. Then, we covered this already, you have the multipath problem. Then you might run into inter-symbol interference. And this means that symbols destroy each other. That means outdoor, you need a larger guard interval. Depending on the guard interval, you can reach certain data rates, and see for the simple BPSK already 520 megabit per second. Whoa, that's already a lot. QPSK, double the points in the constellation diagram, yeah, then you end up 1040, and then depending on how much redundancy you have to integrate, the maximum is something like almost 7 gigabit per second. Under ideal, well, situation, not that much interference, same room, well, line of sight, etc. So, new modulation schemes, different coding, different guard intervals lead to, well, pretty high data rates. Okay. What was possible for this .11 VHT, that's the official name, the high-speed LANs 5 GHz, that's official, well, Wi-Fi 5. So a single link, you can have a throughput of more than 500 megabit per second, but you can go even higher. The point is, okay, we need a bit more bandwidth, so that's also one part, well, one factor you need to consider when it comes to higher data rates. We have MIMO. We go up to, well, 256 QAM. We can use beamforming, so space division multiplexing using MIMO. And then it depends on the capabilities of your access point. So just an example, if you have an 8 antenna access point with a data rate altogether of 6.7, something like this, gigabit per second, you can say, okay, 4 antennas are responsible for my digital TV at 3 point something gigabit, and then 2 more antennas are responsible for a tablet, and then a single antenna for one smartphone, another single antenna for another smartphone. So you can split your data streams for different devices. So altogether, you will end up at this 6 gigabit per second. So this is the Wi-Fi 5 standard. Officially it's called 802.11 VHT in the IEEE terminology. Together with this comes a redefinition of many protocols and many fields and many procedures, etc. Okay, and that's the maximum in the classical .11 standard as you have it today. There are some add-ons, I will come back to this later on. Okay, now think back. Non-overlapping channels. Why is the number of these channels quite important? What is this non-overlapping? Well, then again, there's the user throughput in bit per second, and then the maximum available data rate at the physical layer. So why is the user throughput that much lower? And what contributes to this? Why do we go for higher frequency bands? So what are the advantages and what are disadvantages? And how in the end do we achieve the high data rates? There are several factors contributing to higher data rates.